Hey guys, we're going to take a look at our first section of our textbook today. Now, our textbook is completely online. I'm going to show you how to get to that and give you a few features about the textbook here in just a minute. Today, what we're going to do is look at section 1.1, which is talking about key features of functions. Our entire school year revolves around us talking about different types of mathematical functions. The ways they represent real life, and just the math behind them. One of the things that we're going to talk about is today we're going to look at the key features that will be considered throughout the entire year. On every function that we do, we'll continue to come back to these key features over and over again. I'm going to do my best to keep this video to a minimum if I can. You guys know me, when I get to talking about math, that's probably not going to happen, right? But I will do my best to try to keep this video to a minimum. Remember, you can always pause the video and go, take some notes, try the problems before I go through them. You can always go back and watch them again if you need to. My strong suggestion, and I'll probably have already sent you a message about this when I send you this video, is that you don't just go to the homework and just try to figure it out yourself. Please watch this video and actually learn how to properly talk about the things that we're going to discuss in this video. So, as just sort of a precursor to the video, I'm going to talk about today, we are going to look at these key things. We're going to look at domain and range. For those of you that remember a little bit about domain and range, you may remember that the domain is typically your x values or your inputs. Your range is typically your y values or your outputs. Now, we also have things like independent variable and dependent variable, but we will talk about those, as we go throughout the year. Guys, one of the key features about a function, about the domain and range, is that each input or each x value only has one y value. We've talked about that a little bit already in chapter 1. Or chapter 0 technically, and we're going to talk about that throughout the rest of the year as well. We're also going to talk about intercepts. Now again, we've already kind of mentioned this with linear functions, but we're going to extend that concept to the fact that it can go beyond linear functions throughout the rest of this school year. We're going to talk about positive and negative intervals. Now, I will make a little note here as well on this. We are talking about where the outputs are positive or negative when we talk about positive and negative intervals of the function. Increasing or decreasing. This is where we talk about whether the function is going up or down. Please make sure that you note there is a huge difference between where the function has positive or negative outputs, in other words, the y values, and where a function is increasing or decreasing. You can actually have negative values for y, and the function still be increasing or going up. So please make sure you understand the difference between these two, and I'll talk about that again when we actually do the problems. And finally, we'll talk about the average rate of change. Now, we've talked about specific rate of change for linear functions, but we're also going to talk about how you can look at the average rate of change for a curved function. Now, when you get into pre-cal and calculus, you'll start to zero in on this a little bit more, and you'll start talking about what's called the instantaneous rate of change, meaning the rate of change at any moment on that function, not just the average rate of change over a certain distance. So what I'm going to do is I am going to use the textbook to go through and talk about these, primarily because the textbook has some pretty good examples. Not because I like reading out of the textbook. You guys hopefully know me by now. I'm not that type of person. But because they have some good examples, and also it makes the graphing side of this particular part of the chapter a little bit easier. The fact that Mr. Harrison doesn't have to take the time to graph. And hopefully it'll make this video just a little bit shorter. So, first thing I'm going to show you is how to actually go through and access the textbook. So when you are on Launchpad, you need to find this SAVVAS Easy Bridge. It says Pearson Easy Bridge, SAML underneath it. You need to find this, and you can actually move it around like you do the apps on an iPhone or even an Android device. You can move it around. You need to move this app up near the top, probably next to Schoology, because you need those two things a lot in this course. So you actually have a thing too. I think you can do like a little backpack feature or something that is your most used apps. I'm not really worried about that as long as you can find this. So when I click on this, it's going to take me to a screen that's probably pretty similar to this one. Yours may not have as much going on as mine does, but you have this Envision Custom Algebra 2, or you may have your English there. You click on it, and you should come to this main screen. Now, this main screen is your Pearson textbooks. Again, some of you may have this for English as well, so you may already be familiar with this a little bit already. In the center right here, this is where I will see any assignments that I give to you, and you guys submit them to me. I will see that here. It'll also be the same for you. If I assign you a portion of your textbook, it'll be here in the middle. I will assign the homework on this online textbook as well as giving you a PDF copy on Schoology as well. So you'll have two options. You'll be able to do it through the textbook, which actually gives you a grade, or you'll be able to submit it through Schoology just like we have been all year, or you can even show me on paper. So you'll have multiple options. We've got all these options just in case we were to have to go into another quarantine type thing again. Yay, right? So as you look at this middle column right here, you'll see assignments right here. And I will remind you of this. And if you get lost and you can't find something, please let me know and we'll figure it out together. So underneath the Envision Custom Algebra 2 textbook, you will be able to click on there. Again, you won't have as much stuff as I have on here, but your textbook, it goes by topics. Now the topics are chapters. Basically, instead of calling it a chapter, they call it a topic. You can go straight to this interactive student edition right here, this Realize Reader Algebra 2. If you click on that, it just goes straight into the textbook and you can go page by page. Here's the only issue. Please do not go to this portion here, and there's a page type-in function somewhere. It might even be once you click on one of the chapters, and you click on chapter 1 and you start typing in a page. Oh, I'm not seeing it on here like I usually do. Oh, goodness. Of course, it's not going to do exactly what I thought it was going to do. Or if you click down here on next, yeah, you'll start to see page numbers here. Please make sure that you realize that when it gives you a page number on here, it's not going to line up directly with a physical page that Mr. Harrison is using on the textbook, so be careful with that. But you can go through on this online textbook here, and each one of these chapters, you can click on each one if you need to, whatever chapter we're doing. I will try to label everything as much as I possibly can, as long as I don't forget and make a goofy mistake. Obviously, topic 1 is chapter 1. Underneath this little blue tab over here, topic overview, if you click on topic overview, this is where you see the different sections of the chapter. Again, we're doing 1.1 today, so lesson 1.1 is key features of functions. Notice I titled my notes key features of functions earlier. So when I click on that, then it gives me another little main screen. So this is the thing that kind of stinks about this textbook, is you do have a lot of little menus to click through. But I'm going to also try to give you some little shortcuts here and there. Like I said, when I assign you something online, you can just click straight on the assignment and you'll be fine. Also, I'm not expecting you to read through the textbook necessarily. But when you click on lesson overview, just like you clicked on topic overview, it gives you all the little examples from the lesson. So if you ever get at home and Mr. Harrison has done some examples in class and you want some extra ones, they're usually here. Now today I'm actually using the examples from the textbook anyways. Down at the very bottom is practice and problem solving. Think about it, guys. Practice is where we go for our homework, okay? Think about that's where we're practicing the stuff that Mr. Harrison wants us to. Occasionally, I will have you also look at the do you understand, the do you know how part. So just be prepared. I might throw some of those in every once in a while as well. So each lesson has these examples that we go through. So we're just going to start going straight into here. Now, before we go to that, I'm going to come back over here again. I want to show you just one other little thing about the textbook. I know, guys, you're saying, oh my gosh, we're already 10 minutes in. Mr. Harrison, you said you were going to go quick in this video. I promise. I know. When you click on these topics on the main screen of the textbook, you can also see underneath here each little section. Okay, I've again got a little bit more than you probably going on because I have a lot more resources because I'm the teacher, obviously. This is where you can go straight to the topic or straight to the chapter in the student edition. So if you would rather go that way from the table of contents, clicking on the chapter and then going to the student edition, or clicking on the chapter, finding the topic, the lesson we're on, clicking on the lesson, and then you find the examples of each one. Okay? So if you got any questions, please don't hesitate to ask me. So I know that's 10 minutes of explaining just some basics about textbook and stuff, but I want you to make sure you understand that. You can always come back to this video if you need to. So first of all, let's take a look at domain and range today. So again, one of the reasons that I'm using this today is to help us out, give us a little easier graphing for Mr. Harrison. So when we look at today, what we're looking at is talking about key features of functions. One of the key features of functions is understanding the whole concept of inputs and outputs. The domain is the inputs and the range is the outputs. Or the domain is typically our x values and the range is our y values. Now, we are going to get into this in a whole lot more detail throughout the rest of the year, but there are some functions where there are certain values that you can't plug in. We already kind of talked about this a little bit earlier in the school year, in our few weeks that we've had together, when you had a radical or a square root of an x. We talked about how you can't plug a negative inside there, right? Well, that means the domain for that function would be restricted. That means you can't plug in negative numbers and take the square root of a negative. Now, technically, we can get an imaginary answer for that, an imaginary solution, which is what we'll talk about when we actually get into the more detailed side of radicals and specifically square roots. So, there are times when the function itself limits what values you can plug in. What that also does many times is that limits the y values that come out, the outputs. When we look at a function and we want to determine what the domain and the range is, sometimes that's something we got to think about. What can we not plug in and what can we plug in? So on your notes, if you're taking notes, you may want to write that. The domain, I want you to always kind of think about asking yourself, what can I plug in? Another way to think about that is to think about the negative side of that and say, what can I not plug in? Okay? So, when we talk about the domain, we're talking about the x values, the inputs. What can I plug into the function? So if you're looking at this particular function right here, y equals x squared minus 3, and we want to know what can we plug in, well, we're squaring the x. Guys, think about it. There's no limitation to what you can actually plug in for x. You can plug in whatever you want. And so you could, theoretically, come over here and just start plugging in x values and getting a bunch of y values like we've practiced already in this class. Plugging in things like -2 and -1 and 0 and 1 and 2. Even if you wanted to go to the positive side of things and plug in 3 and 4 and 5, you could plug in a bunch of numbers and you'd get a bunch of y values over here that give you points on a graph, and you can connect the dots. And this one is going to be curved. Obviously, I hope you can tell by our first chapter that this is not linear. It has x squared. So again, to save time, I'm not going to actually go through and make my table of values, but you may have to do that on some of the ones on your homework possibly. You may actually have to plug in some numbers. For us, I'm going to use our textbook because it's nice. It already has it graphed for me. I want you to notice something that we've already kind of talked about a little bit, and it'll be more important next section that we do. Notice the -3 right here. Notice this graph is down 3 spaces right here, and it has that characteristic shape that we saw earlier when we did y equals x squared by itself. When we do y equals x squared minus 3, then it's down 3 spaces. We'll talk about that a little bit more next time. So the graph represents a function because each input has exactly one output. Every x that I plug in over here, I would get one y value. Now you can have some repeats of y values according to what type of function it is. It has this kind of shape. Think about if one of these was opening downward, you would see something like somebody kicking a football through the air. Thinking about Super Bowl coming up this weekend, right? Notice that right here and right here, the football would pass through the same height twice because it's got to go up and it's got to come back down. That's okay. That's still a function. The key thing that a function has to have, like we said, is that each input has to have only one output. So let's talk about what the domain and the range is for this function. So I want you to look at this graph and think about what we plugged in. Is there any limitations on what I can plug in? No, we talked about that, right? So that means the x values for this function can be anything we want it to be. The x can be any real number. Now, we talk about imaginary numbers too later, but we can't do that. We can't plug in an imaginary number. So the x can be any number we want it to be. But what about the y values? Take a look at the graph and physically look at where the y values are. Now guys, it helps again to understand the concept that this is the x-axis and this is the y-axis. Notice that my y values come down here and go back up, but they don't go down here. My function does not touch anywhere down here. That means that the y values or the range is not going to be any number. The y values are going to be here at -3 and up. And so there's two different ways that we can represent the domain and the range of a function. So the x values can be any real number. One way to represent the domain and range is just to use words and to tell people what it is. So we could tell somebody that the x can be anything. Notice the range, though, starts at -3 and it goes up. So when we look at the range, we could tell somebody all the y values are greater than or equal to -3. Notice there's starting to be a little bit there of math, that greater than or equal to thing that we've talked about. But there's two different ways that mathematicians actually represent the domain and range. Those ways are using what's called set builder notation and interval notation. I want you to know both. I know that stinks because that means you gotta know more stuff than just one simple way. But the reason I want you to know that is because there's two different ways you will see it. Your textbook will even use two different ways. Primarily, I think they use interval notation a lot, but you need to know how to deal with both. So let's talk about it. Let's look at what set builder notation looks like and interval notation. So set builder notation basically is sort of like a verbal description or an inequality that describes the numbers. Blah, 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 right? This is what it actually looks like. So notice right here it has this little brackets here, and then it says x with this little bar, and then x is a real number. Notice the same thing with the y. It has y, the little bar, and then it has y is greater than or equal to -3. Now that's what we said. We said x can be any real number, and we said that the y's are greater than or equal to -3. And again, guys, we're physically talking about the graph just as much as we're talking about what we plug in and what we get for y values when we plug in x's. So the way this is read and the way you read it is that the set of all x such that, so I kind of think about the bar as such that x is a real number. The set of all y such that y is greater than or equal to -3. Now I'll go ahead and tell you, Mr. Harrison, primarily when he's using set builder notation, I don't actually use the brackets and everything. I actually just use this one little part over here that's describing the x values and describing the y values. And that is completely fine with me if you do that. I will also tell you that when this little sentence is here, this x is a real number, there's also another little set notation for that that looks like this. X, E, R. Now, actually, that's a Greek letter epsilon, and sometimes textbooks will have a bold R instead of an R with two bars like Mr. Harrison did. I think I showed you this when we were solving equations where an x could be anything. So right here, you have this all real numbers is what this means. X is in the set of real numbers is what it technically means. So you'll see that sometimes Mr. Harrison uses that, or you can use the sentence. The inequalities, I use the inequalities. I use exactly the way it looks. Okay? So this is called set builder notation. Again, it's just using a verbal description or an inequality to tell somebody what the x's can be and what the y's can be. Again, physically describing the graph and describing what values we can plug in, what values we get out when we plug certain values in. That's what domain and range really is. A big thing is people kind of overthink domain and range. Now, it is going to be important for you to understand that the domain is the one that we're going to use a lot because it's going to be the one that we describe some of the other things that I told you we're going to talk about today, like the increasing portions or the positive portions of the graph. We're going to look at those here in just a little bit, and we're going to use domain to describe it. All right, so let's look at interval notation. Interval notation, basically, to me, the reason I don't like it is because it kind of confuses me personally. I'll be completely honest with you, because I start looking at this and I start thinking points. So notice for the domain and the range, interval notation gives you a minimum value on the left and a maximum value on the right to basically give you boundaries for where your x's can go and where your y's can go. Or in other words, the same thing that we're talking about with set notation. Just with set notation, it, to me, I don't know, looks a little more obvious to me when I think about inequalities, just personally. But what this means right here, if you see this little negative infinity and positive infinity, is that all numbers between there work. Or in other words, x can be all real numbers, just like we did with set notation a minute ago. We talked about how x can be anything. The tricky part about these is you have to realize that this little parentheses tells me that it's sort of open-ended, meaning it goes on forever on the end. And so you'll notice that that's kind of like the whole not equal to or equal to part when it comes to an inequality. Take a look at the range. The range looks like this. Remember, we had y was greater than or equal to -3. Again, that just to me is pretty obvious, makes a little bit more sense to me than looking at this. But that's what this means. It means the y values start at -3. That's why you have this little bracket. That's kind of like the equal to part. And then it ends at infinity or goes forever. Notice with the little open bracket there telling me it goes forever. So that's what it's telling me. Now, as far as finding the domain and the range of a graph, what I like for people to do is to think about, yes, what can I plug in when we're talking about the domain? What numbers come out for the range? But I also, like I said, it's physically on the graph. I want you to also be able to think about just looking at the graph and saying, okay, if I'm looking at the x values, this graph right here, when I'm looking at the x values, it touches every x value. Physically, it would touch every one because this graph keeps on going forever. So notice there's an x value, an x value, an x value, an x value, an x value. It keeps going forever. The range, when we think about the range, we are looking at the y values. Notice that this graph does not touch every y value, meaning it starts here, that's the lowest point, and then every y value keeps going that way. So when I talk about the domain and range, that's what I want you to think about. Think about physically on the graph. What I do a lot of times, and I know you guys can't see me right now, what I do a lot of times is kind of put my hand on the graph where something starts and see where it finishes. If it doesn't have a start and a finish, if it goes forever, then it touches everything. All right. Now I know, big long explanation for the domain and range, right? Well, here's the reason I did that. Because the other things that we talk about deal with those values. So you need to have the basic idea of what domain and range is before you move on. I will pop this up on the screen, this comparing the notations to each other with some words in between. This is in your textbook, like I said, and you can find this on the textbook. You can even find the actual picture. If you want to take a picture with your phone right now, you can look at it. But notice that this one talks about, and I'll just pick a couple here, 3 and 4 with brackets means it starts at 3 and it ends at 4. And you could do that with the domain or the range. You could do that with the y values or the x values. But think about physically on the graph what that would mean, x values and y values. Notice one with a bracket on one side and a parentheses on the other. would be 3 is less than or equal to x is less than 4. That means it starts at 3 and has a solid dot there and goes up to 4, right? Well, when we think about the graph, that means you would have, on the graph, you can actually have these little open areas, and we'll talk about those when we get to those later. All right. Again, you can pause that if you need to. So, let's look at a quick little extra example for number 1 here. All right, so look at my graph. Look at your x values. All right, well, the x values are going this way. This is a parabola again, so notice it keeps going forever, right? That means the x values would touch everything. But notice my y values don't go above this. So my y values would be less than or equal to 3. So what that looks like, again, is if you use interval notation, negative infinity up to positive infinity, or that little XER thing Mr. Harrison said, or write out the words, x can be any real number. The maximum value of the function is 3, so this is where you got to be careful. This is the trickiest part a lot of times, is when you do this interval notation like this. This is the other reason Mr. Harrison kind of likes set notation. Notice it starts with the low value and finishes with the high value. And that's going to mess your brain up because your brain is thinking, oh, y is less than or equal to 3. That's what set notation looks like. And again, that's why I like set notation a little better. Now, yes, I know I'm technically cheating on set notation and forgetting this little first bracket part, right? But when you look at this, that's the way my brain thinks. My brain thinks y is less than or equal to 3. Now, some of you may be thinking, that's not the way my brain thinks. Well, if it thinks differently, then try the other one. Try interval notation. It starts at negative infinity forever down below the graph, and then it stops at 3. So if you think of the graph and you think vertically this way, that's fine. You start at negative infinity and you finish at 3. So that's why I have a little bracket at 3. All right. So moving right along. I'm not going to spend a lot of time with this section right here, finding x and y intercepts, mainly because we've already done that, but we are going to kind of come back to this over and over throughout every other chapter this year, where we look at the x and y intercepts of graphs that are not linear. Notice on this one, we've got an y-intercept here at 16 and an x-intercept here at 320. Please do remember that when we talk about these, we're talking about 0, 16, and 320, 0. The x-intercepts and the y-intercepts, remember, have an opposite value for 0. So let me rephrase that again. The opposite value of what you're looking at. For the y-intercept, you have a 0 for x. For the x-intercept, you have a 0 for y. And that's the case no matter what kind of function you're looking at. Now, we've primarily taken a look at linear, and this one is linear also. But we have any type of function out there that we look at, it's the same thing. So notice that also, in this particular example, it also means something. The gas remaining is the y value here, so you have 16 gallons when you're 0 miles of travel. And then as you travel, it should make sense, you use more gas. Now, in real life, that might be not a linear function, but we're using a linear function here to represent this. So 320 miles, we have 0 gallons of gas. In real life, those things can mean things. Sometimes you may run into a graph that has an x-intercept way over here, a y-intercept here, and a x-intercept over here. This x-intercept on this side may not mean anything to the real life situation because it's over here in the negatives, but this one does. Maybe this is something you're taking something and tossing out of a window and it goes and falls down to the ground. Well, the window's pretty important. That's my y-intercept. The ground is pretty important. That's my x-intercept. But this x-intercept on this side is not important to the real life situation. Sometimes that happens. So sometimes that whole concept of domain applies here. In real life, sometimes we're not looking at both sides of the function. So sometimes we restrict the domain on purpose, meaning we say x is greater than or equal to 0, meaning we start here for x is 0, and we go this way. We're not looking at the negative x values because they don't matter to real life. So even though the function actually does include negative values, we don't use it because we're talking about something specific in real life. So domain and range is not just what you see on the graph for any random function, but it also, you have to think about real life as well when you think about domain. All right, moving right along. Let's move on from the intercepts. Identifying positive and negative intervals. Well, what do you mean by positive and negative intervals? Now, guys, like I said, on your homework tonight, you may have to actually graph this using some table of values and actually find a graph on your own. But when I graph this, it ends up being this x squared minus 9, this parabola that we will talk about in more detail in a later chapter, opening upward. Now, what do we mean by positive intervals? Well, the positive intervals is this stuff up here and this stuff up here. And be careful, I know my highlighting is a little off here, but I am not talking about the place where it's the intercept. And this is where you got to be careful. So the intercept right here is not a positive number. It's 0. So when you talk about that, be careful. So let's look, and like I said, I'm using the book because they're a little bit neater than me, but notice the positive intervals, they highlight here in blue for us. Notice that means that the function is above the x-axis. So remember, when we talk about positive or negative intervals, I always want you to be thinking about the y values when we talk about the positive or negative intervals. And I'm sorry about that handwriting. That is worse than anything I've ever done in class. Wow, that doesn't even look like values. Let's try that again. I'm sorry, y'all. That's better. Still ugly, right? So the positive and negative intervals, we're talking about the y values. Where is the function outputs positive? So notice right here, when we look at this right here, we're talking about all the x values that are going this way and all the x values that are going this way. And so notice that they say it is above the x-axis when x is less than -3 and when x is greater than 3. Because this side over here is when x is less than -3, this way. And x is greater than -3, or +3, sorry, guys, this way. Notice it does not include -3 and +3. Why not? Because that's not where the function's positive. That's where the function actually equals 0. So it's not positive there. It's not negative there either. So notice that that would be the set notation, as those inequalities like that. The function, or the interval notation would be like this. From -infinity up to -3. Again, you got to think of moving across the number line until you get to -3. Up here is where the graph is positive. On the other side, from 3 to +infinity, this way, that's where the graph is also positive. So again, you have to make sure in your head that you realize we're talking about where the graph is above the x-axis. So notice again the parentheses here, because it does not include -3 and +3. That's where the intercepts are. All right, so let's talk about where the graph is negative. So I'm going to close that one out. Notice the graph is negative down here. Or in other words, notice that between here and here, in this area between these intercepts, it goes down below the x-axis. So if you look below the x-axis, that is from -3 up to +3. So one way that you can write that is using -3 is less than x is less than +3. Notice again, I mentioned this earlier, but notice again that we're using the domain to describe where the graph is negative. So basically we're saying from here over to here, the graph is down here. So physically pointing at the graph, and I know guys, it's hard when you can't see me at the board because I'd be doing all kinds of crazy stuff with my arms and stuff and pointing at the board and slapping the board and stuff saying, hey, look right here. But you guys can't see that. But from here over to here, my graph is down here. Is everybody with me on that? I hope so. So that is -3 up to +3. That is what we mean by finding the area of the graph where the graph is negative. Notice the interval notation would look like this. And this would be my gripe and my reason for not liking the interval notation as much is notice that it goes right here and it actually looks like a point. It looks like the point -3, 3. That's one of the reasons I don't personally like interval notation, but you can use it. So from here to here, the graph is negative. That's what we're saying. The function or the y values are negative. So again, notice, tying back with what we did on the previous page, notice that there's also two little spots here where the graph is not positive or negative. The graph, the function, the y value is 0 on the x-axis. So the x-intercepts are -3 and +3. But notice, if you know where the intercepts are, then you can also figure out, oh, okay, so if the intercepts are at -3 and +3, that means the positive part is up above the intercepts, and the negative part is below the intercepts. And so it gives me the ability to find where the function is negative and where the function is positive by looking and referencing the intercepts. And so the intercepts actually come into play for my actual domain when I talk about from -3 and less than -3, or from -3 up to +3, and then +3 up to forever or infinity. So it gives me the ability, if I know where those intercepts are, that really is what helps me find the intervals. All right, so real quick, I'm going to show you another quick example. Notice this one here. Oh, and this is a good one. I forgot this one was here. Notice that it has -x² plus 9. So we actually have to use this little slider right here to move it up until you get to 9. So you can see, oh goodness, they use Desmos to help us get up to this little spot here to get it to 9. And then it helps me to see that, again, on this one, happens to be the same ones here. -3 and +3 are my intercepts. So where is it positive? Well, the function is positive between -3 and +3. So the positive portion of the graph is from -3 up to +3. Notice that the function is negative, and I'm going to see if I can slide this thing up, if it'll let me. Yeah, there we go. And it moved my points around. I forgot I'd written over the top of it. Sorry, guys. So notice my negative portion is over here, but that's any value that's going this way. That's any value that is less than -3. So notice it's got this for interval notation. It would be less than -3 for set notation. Notice it's also negative over here. The graph is negative over here. So it's going this way. That's what looks like this in interval notation from 3 to infinity, or x is greater than 3 on this side. So again, what we're looking at, guys, is physically where the graph is positive, where the graph is negative. All right, we got two more things. The first one is, where does the function increase? Where does the function decrease? Now notice this one right here, and we're just going to kind of see if we can review a little bit here real quick. This is an absolute value. Notice it has a negative in front of the absolute value, but the 2 is over here. That may weird you out a little bit, but if you did the commutative property and switched it around to +2, you would realize that I have an absolute value that is opening down. The vertex would be at the point 0, 2, and it would be opening down this way and opening down this way. That's what we did in the previous chapter. And let's check it. Oh, yep, there we go. There it is, opening down up here. 0, 2 is my vertex. Remember I said earlier in this lesson today, you could also make a table of values, plug in some numbers, and get some points. So if you forgot how to graph, guys, there's always the option. If you forget how to graph, you can use a table of values to help you get some more points. So we want to know where this function is increasing and where it is decreasing. This is where you have to be careful. increasing and decreasing do not mean the same thing as positive or negative. Increasing means from left to right. Decreasing means from left to right. Think about the slope, and it may help you a little bit. Trying to talk and write at the same time, not working, is it? From left to right, what is it doing? If it's going up, that's increasing. If it's going down, that is decreasing. And guys, it doesn't have to be a straight line to do that. So notice on this side of the graph is going up. This side of the graph is going down. So this is increasing, this is decreasing. All right, so let's see. I want you to try and see if you can do it on your own. Pause the video here and see if you can tell me what are remember the domain, the x values, where this function is increasing. Notice over here, like I said, it's going up. Even in the table of values, you can see it going up. So what values of x, not just from the table, from the whole function, what values of x make this thing go up? And what values of x make this thing go down? That's what we mean by increasing or decreasing. So pause the video and try it real quick. All right, so hopefully you paused the video and you tried it. So right here, notice this side of the graph is going up, but that means this arrow goes forever. So that means I start at negative infinity and I go up to go. Oh, wait, notice. This is also important. Let me point this out. There's a maximum value right there at the vertex. That's when it changes directions, doesn't it? So when you look at this and you say, okay, it goes from negative infinity, goes, stops, and then it changes direction. That means 0 is the x value right there. 0 is where it changes direction. And so this would be my my interval notation. My set notation would be x is less than 0. That means everything this way is where the graph is increasing. So guys, I know there's a lot of terms in this section, so you've got to be careful and you've got to make sure you keep all these terms separate. I know it's tough. That means you may have to watch this video once, maybe twice, maybe pause, maybe rewind. You may have to. All right, well, we'll look at the other side. Okay, so now we're decreasing forever, right? So where does it start? Well, it starts at 0 like this one ended, and then it keeps going forever. So interval notation would be from 0 up to infinity. Set notation would be x is greater than 0. So basically what we're saying is if you plug in negative numbers, the function's going to be increasing. If you plug in positive numbers, the function's going to be decreasing because that's what it does physically on the graph, guys. Now, the tricky part here is realizing that right here at 0, that's not increasing, that's not decreasing. So when you get to a point like that, where it switches direction like that, that's a maximum value or a minimum value. In order for a function to have an increasing part and then a decreasing part, it has to have a change in directions at a maximum or minimum value. So sometimes you'll see some textbooks call that an extrema or an extreme value. So notice, let's check our work here. Let's make sure we got it right. Increasing portion, yeah, we got that side right, from negative infinity up to 0. Yep, we did it, good. Decreasing portion is on the other side. The decreasing portion is over here, it's going down. And notice that it is 0 to infinity, good. Now, again, guys, you'll see Mr. Harrison write a lot of this little set notation more than the interval notation, but I do want you to be aware your textbook likes to use interval notation a lot. Notice also here we got a maximum point there at the vertex. A minimum point would be where it changes from decreasing to increasing. So you would be going down and you come back up. When you go down and come back up, think about the parabolas that we did earlier. That would be a minimum point. So this side of the parabola would be decreasing. This side of the parabola would be increasing. That's what we mean by increasing and decreasing functions. So be careful with those. Make sure you're paying attention to what it actually means from left to right, going up, from left to right, going down. Now, I do want to warn you, too, about some functions that look like this. Take a look at this kind of weird function like this. Now, in your head, some of you might accidentally look at this and say, right there, it changes directions. Well, notice that it changes and flexes, sort of, yes, but it doesn't actually change from increasing to decreasing. Notice this graph, when I drew it, I was drawing a line that goes up the whole time. I never stopped going up. So this one would actually be increasing for the whole thing. So this thing would be increasing for all real numbers. Remember that little XER thing that I gave you? Or you could say negative infinity up to positive infinity, meaning you go from the lowest negative number up to the highest negative number you can think of, which actually you'd still go farther. That's what infinity means. All right, so that's where a function is increasing or decreasing. All right, so the last thing I want to show you is when you have a average rate of change. Now, when you have a function that is curved over a certain area, you can actually find a point that's right here and a point that is, and I'm going to try to get it on the line as much as I can. I probably will use the textbook here in a second anyways. This has an x value wherever a is. This has an x value wherever b is. This has a y value of what you get when you plug into the function f of x. Now we also have, remember, this could be x squared, this could be x cubed, this could be x to the fourth. We don't really know what this one is. I can tell you it's probably not one of these just because I've done a lot of math and you haven't, right? Woohoo, yay, Mr. Harrison, quit talking good about yourself. All right, so anyways, when I plug in a to the function, I get my y value. When I plug in b to the function, I get my y value. So this is my x, this is my y. This is my x, this is my y. How do you think you would find the average rate of change? How do you think you would find the rate of change between these 2 points? If you're screaming at your screen, slope, Mr. Harrison, slope, Mr. Harrison, slope. I know it, slope. You're actually right. So to find the rate of change, just like we normally do for a linear function, we find y2 minus y1 over x2 minus x1. Basically, it's the same idea. Right here, you've got where the starting and the ending points are, just like we just talked about. You can find the change in y values by subtracting the y value here minus the y value here. You can find the change in x values by subtracting the x value here minus the x value here. Guys, that's the same thing we did when we were doing that y2 minus y1 over x2 minus x1. It's the same thing. The only difference here is we're talking about a random function that is not linear, and then it gives us the rate of change from here to here. But notice what it gives you. It gives you this linear rate of change also. And that's where you've got to be careful, because in the real world, sometimes you're going to get into some that are actually asking you to find, okay, what's the rate of change right here? 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 You have multiple rates because it curves. In pre-cal and calculus, we call that the instantaneous rate of change. So the average rate of change is very similar to just a linear equation. You're just finding what is the average change across that little curved distance right here. So essentially, you're still just finding a linear rate of change. But in the real world, you may see some things where you have to find the rate of change more than once. And you're finding it at different little points here across that whole area. So that is our lesson for today. That is some key features of functions that you will see. Again, your homework will be based off of the practice and problem solving that is in the textbook. Now, the practice and problem solving, it's not going to be right here, is it? Yep. Okay, so let me go back over here, see if it's still open. Remember when we had the lesson key features of functions open, the practice and problem solving will be the bottom little tab there. it'll open up a PDF page of your textbook, and this is where you will see the problems. I will also put this PDF onto Schoology as well, so you'll have a copy of the PDF, and then I will assign the numbers in the textbook, so when you click on the textbook, you will be able to see that assignment right here in the middle of the screen underneath classes. So you'll be able to see the assignment that I assign here. You can do it on the textbook. It'll actually give you a grade and see how you did. Or you can take the PDF off of Schoology and you can do the problems on pieces of paper. Most of you are probably going to do them on paper anyways, even if you do the online version. And then you can submit a picture to me. Or you can bring it to class next time and show me. So, hope you guys have a great weekend. Cheer Tom Brady on, or Patrick Mahomes, whoever you prefer, for the Super Bowl. So, I hope to see you guys get good and safe and well on Monday.